We're going to look at this example finding the absolute max and min of this function of two variables over this closed bounded domain. So the first step is going to be to graph what the closed bounded domain looks like. And we did this in class, so just put a quick reminder here. Here's what A looks like. So now let's get a visual of what we're actually trying to do in the problem. The function z equals x squared plus y squared is an elliptic paraboloid that opens up. So you can picture that as like a little bowl opening up. And instead of looking over the whole xy plane, we're just going to restrict the domain to be over this region A, including the boundary of A. So here's a visual of what that looks like. So I want you to imagine that maybe you're hiking along this paraboloid, and you're just going to hike where your domain values are the boundary of A or the inside of A. And so if we try to trace that out on the actual paraboloid, here are a couple more pictures. There you can see the actual values on the paraboloid along the boundary of A, and then a couple more pictures just from a few different angles, so you can try to see what we're trying to find. And just from a quick glance, it appears we can find the absolute max of this occurring, let's look in the bottom left picture. That looks about to be the highest point, at least within our restricted domain, the highest point that you're able to get on the paraboloid. And then the lowest point within our domain A looks to be right here at the origin, just the bottom of the paraboloid. So that's what it appears from the picture, but now let's dig into this analytically and see how we can find this same result mathematically. I'm going to flip to a new page here, so just a reminder of the function we're dealing with. So the first place the first thing we want to check are for any critical points. And so that's going to occur wherever our gradient is equal to 0 or where the gradient doesn't exist. And this should be the 0 vector because the gradient is a vector. Put the vector sign. Okay, so if the gradient is 0, that's going to imply that the partial derivative with respect to x is 0 and that the partial derivative with respect to y is 0. And that's going to give us the origin as a potential point where I have an absolute max or an absolute min. So we're just going to be collecting a list of potential points throughout this process. I'm just going to call this one point 1. We're going to collect all of them at the very end. We'll compare to figure out which one gives us the largest and smallest values of z. So point 1 is here, and I'm going to go label it again on our picture of A. And one of the things to check as you do this is as you find a point, you just want to check and make sure it's actually in the region that your domain is restricted to. So 0, 0 is along the boundary of A. And we're just calling that here. This is our first point, point 1. Okay, so now we're going to look along the boundary itself. And I'm going to start along the top part of the boundary, so along the parabola. We're interested along that top parabola, flipping to the next page here, that we want to find potential places where z is going to be a maximum or a minimum. So along y equals 2 minus x squared, then we can rewrite z. Z is x squared plus y squared, so that's going to become the following. And we know that we're just looking along the top boundary of A, and so along that boundary x is restricted just from -2 to 1. Okay, so I've just rewritten z all in terms of one variable because we're just looking along the top boundary. Now we're going to take this back to a Calculus 1 problem, so I want to find any possible max or mins of z along in this region. So as we know from Calc 1, when we have a bounded interval where we're trying to find max or mins, we first look at where the derivative was equal to 0 or where it does not exist. And then we're also going to look at the endpoints. Okay, so we're going to need to move to a new board. So let me copy over what we have so far. Along y equals 2 minus x squared, We can rewrite z just as a function of x. Now we're going to need to find where the derivative of this is equal to 0. So dz dx is just given by this, and we're setting this equal to 0. So that implies we can do some factoring here, and we're going to get x is either equal to 0 or x is plus or minus the square root of 3/2. Okay, so now we need to go back and remember we're trying to gather points in our domain in the xy plane. So if x is 0, then y, we plug back up to the very top equation, then y is going to be 2. So now we want to go back and look to see, you're going to go back 2 pages here and make sure that that's actually in our region A, and we can see it is. So we're going to call that point 2. So here's point 2 at 0, 2. And that's the second possible place where we might have a max or min. Oops. Okay, now let's go back. So we have 0, 2 is one of our possibilities. Now notice if x is equal to positive square root of 3/2, we have to go back and look. If you come back and look over here, you notice when x is positive square root of 3/2, we will no longer be in our region A. So that is not included in our domain. So we can ignore that one. But let's look at the case where x is equal to negative square root of 3/2. If x is negative square root of 3/2, you can come back over here. That is going to be within our domain. And we need to find the y value that matches to that. So I'm going to take this and plug it back into my equation for y at the top. When I do that and simplify, I'm just going to get 1/2. So we're going to call that point 3. And let's go back to A and label that. Okay, so far those are 2 spots along the top boundary where we might have an absolute max or min. The last thing that we need to check along that top boundary are the endpoints. We can see our interval x goes from -2 to 1. So if x is -2, we plug that back in to our equation. At the top, that tells us that y is going to be -2. We'll call this our 4th point, so let's go back over and label it here. And then we'll check the other endpoint, which we can see is going to happen right here. That's going to happen when x is 1. Let's go back and see mathematically what that's going to make y. We can see when x is 1, if we plug it back up into here, the top, that y will also be 1, and we call that 0.5. Okay, we've now checked every possible place along the top boundary, and so the last thing we need to do is check along the bottom boundary, along the line y equals x. And it's going to be similar to what we just did. Along y equals x, then we have z. Z we know is x squared plus y squared, so z is going to become x squared plus x squared. And so we're just going to get 2x squared. And again, we're going to limit x to go from -2 to 1. Okay, so now we're just going to find possible max or mins of 2x squared. Again, we're going to look for where the derivative is 0. So that's going to imply 4x equaling 0, or x equals 0. If x is equal to 0, we come back up to the top, y is equal to x, so that would mean that y is also 0. But this takes us back to point 1. We already have this point. And then we just need to check the endpoints. But we notice we already have the endpoints. We counted them before on the top interval. We had 0.4 and 0.5. Those are both the endpoints. So we now have gathered all the possible points in our region A where we may have an absolute max or an absolute min. And now we're just going to need to evaluate the function at each of those points and figure out where it's biggest and where it's smallest. So I want to point out for this particular example, all of our potential points ended up being on the boundary. but that's not necessarily always the case. So you always do need to start by finding where the gradient is 0 or where it doesn't exist, like we did here. And that will help you find all the potential points inside the region. And then you're going to look specifically along each boundary separately. Okay, so now we're at our final step. Now we're just going to evaluate the function at each point that we found so far and figure out where the function is greatest and where it's smallest. So at point 1, we can see that z is just going to be 0. Point 2, we can see that z is going to be 4. At point 3, we can see that z is going to be 7/4. And then at this endpoint here, we're going to get that z is equal to 8. And then finally at 1, 1, we get that z is 2. So then we just compare the values and we can see that the absolute minimum occurs at the origin, like we saw from the picture. And we can see that the absolute maximum occurs at this corner, -2, -2. And the absolute max is the value 8. And this corresponds back to what we noticed originally in the picture, that this corner here, -2, -2, in the domain appeared to be where we got the greatest value, and that the origin was our absolute min. And that's it.